Uranus, the seventh planet from the Sun, is tilted on its side by approximately 98 degrees. This makes it unique among the planets in our solar system, as none of the others are oriented in this way. Discovered by William Herschel in 1781, Uranus was initially thought to be a comet due to its unusual behavior. However, it was later confirmed to be the first planet discovered with the use of a telescope. Uranus has a system of 27 known moons, including 5 major ones: Miranda, Ariel, Umbriel, Titania, and Oberon. In addition to its moons, Uranus is surrounded by a system of 13 known rings. The unique tilt of Uranus raises several questions about how this orientation affects the planet's climate and overall structure. How does such a dramatic tilt impact the seasons on Uranus? What are the implications for its atmosphere and weather patterns? By exploring these questions, we can gain a deeper understanding of how this celestial body defies our expectations and reveals the fascinating complexities of our solar system. This is Uranus, the sideways planet, waiting to reveal its secrets one at a time. Before we begin, a small request. Most of the people listening tonight aren't subscribed. If this channel has ever helped you drift off, take a moment to subscribe. It's free, it helps this channel more than you'd think, and you can always change your mind later. And if you feel like it, leave a comment telling me where in the world you're listening from and what time it is where you are. I love reading them. One more thing before we begin. I'm also a co-founder of a sleep app built to be the most affordable one out there. No ads, ever. Just sounds and stories made to help you sleep. It may not be released yet as this video goes up, but if you're watching a little later, it might be out by now. Just search for it. It should be easy to find. It works on iPhone, Android, and everything in between. Downloading it is the best way to support this channel. The temperature in Uranus's upper atmosphere can drop to 2224 degrees Celsius, 3071 degrees Celsius. Imagine a globe turned on its side. That's what Uranus looks like in the night sky. This unusual orientation not only affects how much sunlight reaches different parts of the planet, but also influences its complex magnetic field. This means that the planet's magnetic north pole is not aligned with its rotational axis, but instead is offset. Astronomers aren't sure why Uranus has such a low core temperature, but they think it's related to this bizarre rotation. Perhaps the collision that set Uranus on its side released much of its internal heat, leading to this icy core. But what effect does this have on Uranus's climate and seasons? Stay with us as we delve deeper into the mysteries of this sideways planet. The primary culprit for this deep freeze is Uranus's distance from the Sun, a staggering 2.87 billion kilometers away. That's more than 19 times further than Earth's journey around our star. But it's not just the distance that accounts for this icy realm. Uranus also lacks significant internal heat. Unlike planets like Jupiter and Saturn, which have warm cores that generate considerable heat, Uranus is largely composed of ice water, methane, and ammonia. These frozen materials are believed to make up the majority of its interior, creating an insulating layer that prevents any substantial warmth from rising to the surface. Adding to this chilly mix is the planet's unique atmospheric composition. Primarily made up of hydrogen and helium with trace amounts of methane, these gases contribute to a blue-green tint seen from space, but do little to trap heat. In contrast, Earth's atmosphere is thick with oxygen and nitrogen, which effectively captures sunlight to create a warm blanket around our planet. To put this into perspective, Uranus's average surface temperature can dip as low as 1870 degrees C, C324 degrees C5, making it feel almost unimaginably cold to anything that might try to call this world home. Even more dramatically, temperatures in the thermosphere, the uppermost layer of its atmosphere, can reach an astonishing 370 degrees Celsius and 223 degrees Celsius. This makes even the coldest regions of space seem comparatively balmy. This is not some distant, abstract planet. This is Uranus, a world where one pole basks in perpetual sunlight for over 2 decades, while the other endures an equally long night. During this extended summer, the illuminated pole receives a constant barrage of solar energy. Meanwhile, the dark pole remains shrouded in an uninterrupted winter's chill. To put this into perspective, consider that Uranus takes about 84 Earth years to complete one orbit around the Sun. That's nearly a lifetime for us. And as it slowly makes its way around the Sun, the axis of Uranus remains almost directly pointed at the star. This alignment means that one pole is always sunlit while the other languishes in darkness. This peculiar orientation leads to extreme seasonal variations. During summer, temperatures can soar as high as they do on Earth, albeit without the moderating influence of large bodies of water. Interestingly, despite its distance from the Sun, about 1.9 billion miles, 3 billion km on average, Uranus receives only about 4% of the sunlight Earth does. This faint sunshine, combined with Uranus's internal structure, allows the planet to release its heat more efficiently than other planets. Yet, something about Uranus's internal structure makes this process particularly effective. But what truly sets Uranus apart is the sheer duration of its seasons. Imagine standing on the sunlit pole, basking in endless summer for 21 years straight. During this prolonged summer, temperatures remain stable and relatively warm. However, when the season finally shifts, the transition is abrupt and dramatic. As Uranus tilts towards the Sun again, the other pole emerges from its 21-year night into a new dawn. This cycle repeats every 84 Earth years. These extreme conditions shape Uranus's weather patterns and day-night cycles, making it a world of stark contrasts. This planetary oddity is largely due to Uranus's extreme axial tilt, which causes it to roll around the Sun on its side. This unique orientation gives rise to severe weather patterns and bizarre climate conditions that defy our expectations of celestial bodies. Scientists believe these strong winds are a direct consequence of Uranus's peculiar axial tilt and the extreme seasonal contrasts it causes. As Uranus rolls through space, these powerful winds shape its weather patterns and contribute to the stark contrasts that make this planet a world of extremes. But what do these extreme wind speeds mean for Uranus's day-night cycles? Let's explore how these weather patterns affect the planet's unique light and dark periods. The tilt of Uranus isn't just any old incline. It's a radical sideways lean, causing the planet to roll around its orbit like an oversized top spinning off balance. This extreme orientation has profound effects on the polar regions of Uranus. The southern hemisphere experiences the exact opposite. Summer daylight fades to a long, dark winter night. These extreme seasonal variations are unlike anything we observe on Earth. Imagine, if you were standing at Uranus's North Pole during the height of summer, you'd see the Sun creeping slowly across the sky over 21 long years. Conversely, when winter rolls around and the North Pole is cast into a 21-year-long night, temperatures plummet to D197 degrees C, a drastic swing that could freeze any visitor solid. This dramatic temperature difference between the sunlit and dark sides of Uranus is a direct consequence of its unusual orientation, which defies our conventional understanding of day-night cycles. These extreme conditions shape the planet's weather patterns and climate in unique ways, leading to a world that's as bizarre as it is intriguing. Uranus's unique tilt not only alters its day-night cycles, but also drives the planet's entire climate, leading to an environment that is both extraordinary and awe-inspiring. While Voyager 2's flyby of Uranus in 1986 provided the first detailed images and data about this enigmatic planet, much remains unknown about its complex climate and structure. Scientists are eager to unravel the mysteries of this ice giant, with upcoming missions promising new insights into its unusual orientation and environmental dynamics. One such mission is set to deploy advanced instruments that will penetrate Uranus's thick atmosphere, uncovering secrets hidden within its complex layers. These tools will also shed light on the planet's magnetic field, first detected by Voyager 2 during its flyby, and how it interacts with the solar wind in this unique environment. Moreover, high-resolution imaging systems will capture detailed views of Uranus's rings and moons, providing a clearer picture of how these components influence the planet's climate patterns. The aim is not just to gather data, but to piece together a more comprehensive understanding of Uranus's dynamic weather systems and their interplay with its axial tilt. As we look towards the future, these upcoming missions signal a new chapter in our exploration of this fascinating world, one that promises to unveil the true nature of Uranus's enigmatic climate and structure. Interestingly, while other planets like Earth have more stable magnetic fields due to their regular rotation, Uranus's retrograde rotation, where it spins from east to west, further complicates the dynamics of its interior fluid. Nevertheless, the exact reasons behind the magnetic field anomaly remain a mystery. Future missions promise to delve deeper into this enigma, potentially unraveling the intricate relationship between Uranus's tilt and its magnetic behavior. By exploring these peculiarities, we gain a deeper understanding of how celestial bodies like Uranus defy our expectations. Its unique orientation not only influences its climate and seasons, but also shapes the very fabric of its internal structures. This isn't like Saturn's vast, icy rings. Uranus's rings are faint, dark, and narrow, circling a planet that rolls on its side. Their unusual formation is attributed to Uranus's extreme axial tilt, which affects the dynamics of these rings in fascinating ways. Scientists believe that collisions and interactions within this system have shaped its current configuration over billions of years. The most prominent ring is the Epsilon ring, a dark band just 20 kilometers wide, filled with tiny particles no larger than a grain of sand. Surrounding it are narrower rings that appear as mere shadows in the vast cosmic landscape. Their stability is maintained by the gravitational influence of Uranus's 27 moons. The extreme tilt also causes unique seasonal variations in sunlight exposure, which affects how these rings form and interact over time. During this period, some rings might experience prolonged darkness or intense light, leading to shifts in their composition and structure. Imagine the Epsilon ring during such a season. The tiny particles might absorb more sunlight than usual, slightly altering their properties over time. These subtle changes highlight how Uranus's unusual orientation directly influences the behavior and dynamics of its rings. The tilt also affects wind patterns on the planet, which can further impact ring stability and alignment. Understanding these intricate interactions helps us grasp how celestial bodies like Uranus defy our expectations. Even their rings are shaped by the planet's unique orientation. Beyond the striking sight of Uranus's rings, another fascinating phenomenon is at play: the planet's unique wind patterns. Wind is an often overlooked yet crucial aspect that shapes a planet's climate and seasons. This extreme speed is driven by the planet's unusual orientation and the way heat is distributed across its surface. The strong winds contribute to Uranus's complex weather systems and climate patterns. Uranus's winds are not just swift, they are also highly directional, shaped by the planet's extreme axial tilt. This results in unique wind patterns that flow from one pole to the other. The temperature differences between Uranus's poles due to its tilt create significant variations in air pressure, which in turn drive these powerful winds. These wind patterns are further influenced by the planet's retrograde rotation. Uranus spins from east to west instead of the typical west to east. This unusual spin and tilt create a dynamic interplay between the planet's wind patterns and its seasons, leading to unique weather phenomena that span across Uranus's vast surface. In this cosmic dance of wind and planetary tilt, Uranus continues to surprise us with its intricate interplay between rotation, wind patterns, and the extreme conditions it experiences. These moons are not simply passive observers of Uranus's peculiar climate. They actively influence the planet's atmosphere and weather patterns through a series of intricate orbital behaviors. For instance, Miranda, the smallest of these major moons, possesses an elongated path that takes it closer and farther from Uranus's poles. This eccentric orbit causes gravitational tugs that can alter wind patterns, creating eddies and minor storms as the moon pulls on the atmosphere. Meanwhile, Ariel, the brightest of Uranus's moons, has a more circular orbit but still plays a significant role in shaping the planet's climate. Despite its stability, Ariel's path generates regular tidal forces that can affect Uranus's atmosphere, contributing to the formation of distinctive weather patterns. Umbriel and Titania, two larger moons, exhibit similar gravitational effects due to their orbital paths around Uranus. Oberon, the outermost of these major moons, has a significant impact on Uranus's climate due to its distant yet stable orbit. Its consistent gravitational pull helps maintain the planet's overall atmospheric stability, mitigating some of the extreme weather conditions caused by Uranus's tilt. Their gravitational tugs and tidal forces not only shape Uranus's weather, but also underscore the complex interplay between the planet and its satellites. By understanding these orbital behaviors, we gain insight into how the broader system around Uranus is affected by the planet's tilt. Thus, the moons of Uranus are not merely passive companions. They are active participants in a dynamic celestial ballet that shapes and reshapes the planet's climate with each orbit. In this way, Uranus's unique tilt extends its influence, creating a complex interplay between the planet and its icy moons that is as awe-inspiring as it is intricate. These powerful winds shape intricate weather systems and storms, which can span the entire planet. Observations from spacecraft have captured images of vast storms that encircle Uranus like a belt, contributing to its distinctive blue-green hue. Conversely, during the winter solstice, when the other pole is in complete darkness, temperatures plummet to extreme lows. This severe cold creates conditions that are among the harshest in the solar system. The complex interplay between prolonged light and darkness, coupled with Uranus's unique atmospheric composition, results in a climate that is as remarkable as it is alien to our understanding. This extreme orientation not only shapes Uranus's polar regions, but also extends its influence across the planet, creating a complex and intricate climate that is as awe-inspiring as it is unique. Uranus's extreme tilt of 98 degrees profoundly impacts its ionosphere, the region of charged particles in its upper atmosphere. This layer plays a crucial role in filtering out harmful radiation and reflecting radio signals back to Earth. As Uranus rotates on its side, it presents a unique surface to the solar wind, the stream of charged particles emanating from the Sun. During this prolonged daylight period, Uranus's ionosphere becomes highly energized due to the intense solar radiation. This can lead to the formation of massive plumes of charged particles that extend far into space. The complex interplay between Uranus's tilted magnetic field and the highly charged plumes in its ionosphere results in unique patterns of auroras that are not seen on other planets. This behavior is a direct result of Uranus's sideways rotation and the planet's unique orientation in space. By studying Uranus's ionosphere, we gain insights into how extreme orientations affect a planet's upper atmosphere and interactions with cosmic elements. The winds of Uranus tell a unique story, shaped by the planet's extreme axial tilt and the resulting sideways rotation. These winds are not merely a surface phenomenon, they span the entire globe. These extreme conditions lead to unusual storm systems that can span the entire planet. For example, large storms on Uranus are often observed near its poles during periods of prolonged sunlight. The length and intensity of these storms can be attributed to the planet's peculiar orientation and the resulting atmospheric dynamics. Scientists believe that Uranus's unique tilt plays a significant role in shaping these anomalous weather patterns. By studying these winds and storm systems, we gain insights into how extreme orientations affect the global atmosphere of Uranus. This demonstrates the far-reaching effects of Uranus's sideways rotation on its overall atmospheric structure and climate dynamics. Observe the swirling patterns in Uranus's sky as if the very air has been put into a spin. These aren't just ordinary clouds. They are peculiar formations born of Uranus's unique tilt. With such a drastic orientation, wind patterns and cloud formations are subject to extraordinary variations. Imagine a continuous belt of clouds wrapping around Uranus, a band so expansive it would dwarf any weather pattern on Earth. The complex interplay between the planet's extreme tilt and its fast-moving winds results in intricate atmospheric features that defy expectation. These formations are not merely aesthetic. They play a crucial role in Uranus's weather and climate systems. As the seasons shift on Uranus, these cloud formations migrate across the planet, carrying heat and moisture with them. Through their intricate dance, these clouds are integral to maintaining a semblance of balance in Uranus's unusual climate. And so, the peculiar sideways rotation of Uranus not only shapes its overall structure, but also intricately weaves itself into the very fabric of its atmospheric features. Uranus's retrograde rotation, spinning east to west instead of the usual west to east, is a peculiarity that defies our expectations for celestial bodies. Astronomers believe that this magnetic field's tilt could be a result of Uranus's retrograde rotation and its bizarre axial tilt. Imagine the Earth with its North Pole somewhere in the Atlantic Ocean, while the South Pole is situated over Asia. Such an alignment would cause dramatic shifts in our planet's climate and weather patterns. Despite these conditions, Uranus maintains a surprising level of stability. Its complex magnetic field and the intricate dance of its internal layers create a resilient structure that withstands the planet's extreme environment. This peculiar orientation not only affects the planet's climate and seasons, but also exerts a significant influence on its magnetic field, strength, shape, and interaction with the solar wind. The sideways spin of Uranus creates an intricate dance within its interior layers, which in turn shapes this unusual magnetic environment. Imagine the Earth's magnetic field as a smooth and balanced sphere. Uranus's is more like a lopsided, wobbling donut. This peculiar magnetic orientation allows the solar wind to interact with Uranus in unique and unexpected ways. As the solar wind streams by, it encounters this off-kilter field, creating a dynamic interplay that is unlike anything seen on other planets. This interaction reveals the profound impact of Uranus's tilted axis on its overall magnetic structure and environment, illustrating how a planet's orientation can defy our expectations of celestial bodies. The extreme tilt of Uranus's axis introduces an unpredictable element to its atmosphere, one that sets it apart from other planets in the solar system. This peculiar orientation leads to dramatic variations in atmospheric pressure across different regions of the planet. As a result, the lit side experiences intense solar radiation, creating higher atmospheric pressure. On the dark side, the absence of sunlight causes lower atmospheric pressure due to reduced heat and energy. The strong winds and unique weather patterns are further influenced by the presence of methane in Uranus's atmosphere. Methane absorbs sunlight differently than other gases, contributing to Uranus's distinctive blue hue and complex climate dynamics. Despite the harsh conditions, these atmospheric interactions create a fascinating interplay between light and darkness. Uranus's tilted axis thus not only shapes its magnetic field, but also dictates the intricate dance of atmospheric pressure. Understanding these processes offers a glimpse into how a planet's orientation can profoundly influence its entire environment. In the North Polar atmosphere, temperatures can plummet as low as 224 degrees Celsius, 371 degrees Celsius, during the long, dark winter solstice. Meanwhile, the South Pole basks in constant sunlight for 42 years straight, with temperatures reaching up to 19.7 degrees C, 325 degrees C for Certi. These winds are driven by the heat imbalance between the two poles, creating a global circulation that shapes the planet's climate and weather systems. The extreme axial tilt also affects how sunlight reaches different regions of Uranus. This magnetic field helps to trap and contain the planet's atmosphere, preventing it from being stripped away by solar winds. The interplay between Uranus's unique orientation and its magnetic field creates an intricate climate puzzle that continues to captivate scientists. The troposphere is the lowest layer, closest to the planet's surface. It contains hydrogen and helium, with trace amounts of methane that lend Uranus its distinctive blue-green hue. Above the troposphere lies the stratosphere, where temperatures start to rise due to the absorption of sunlight by the methane molecules. These atmospheric layers interact in ways that are shaped by Uranus's unusual orientation. For instance, the methane in Uranus's atmosphere absorbs sunlight differently than the hydrogen and helium. This unique absorption pattern contributes to the planet's extreme temperature variations. Ammonia, another trace gas in Uranus's atmosphere, can form into clouds that reflect sunlight back into space, further influencing the planet's climate patterns. By exploring Uranus's atmospheric composition and its layers, we gain insights into how the planet's unique orientation influences its climate patterns, creating a celestial puzzle that continues to fascinate researchers. This understanding helps us appreciate the intricate dance of Uranus's atmosphere and its profound effects on the planet's overall structure. As we continue to unravel these mysteries, the more we come to realize that Uranus is not just a distant ice giant, but a complex world with its own set of rules and rhythms. The zonal winds on Uranus are affected by the planet's extreme axial tilt, leading to unusual wind patterns that can span the entire globe. These winds include super-rotating prograde winds and retrograde winds, which flow in opposite directions. During this time, the zonal winds on Uranus are driven by the intense heat and sunlight that bathe one side of the planet. These winds play a crucial role in redistributing heat and atmospheric gases across Uranus's surface, creating dynamic weather patterns. This complex interplay of wind patterns, temperature variations, and seasonal extremes is a testament to the unique dynamics that govern Uranus's atmosphere. By understanding the zonal winds and their role in shaping Uranus's climate, we gain a deeper appreciation for the celestial dance that takes place in this far-off world. These winds are more than just atmospheric phenomena. They are essential to maintaining the delicate balance of Uranus's climate and weather systems. Uranus's atmosphere is a critical player in shaping its climate and weather patterns, and understanding atmospheric pressure on this planet reveals a unique story of extremes and resilience. As you journey upward through Uranus's atmosphere, the air grows increasingly thinner. This is due to the planet's extreme axial tilt, which causes atmospheric pressure to vary dramatically with altitude and location. At higher altitudes, where the atmosphere is thin, pressures are lower. This creates ideal conditions for the formation of intricate cloud patterns that play a crucial role in Uranus's weather systems. The complex interplay between pressure and temperature on Uranus highlights how this planet's unusual orientation creates a climate that is anything but ordinary. By understanding these intricacies, we deepen our appreciation for the delicate balance of atmospheric pressure in shaping Uranus's extraordinary environment. Uranus's magnetic field, unlike Earth's, is not only tilted, but also offset from the planet's center by a third of its radius. This unique configuration creates a dynamic interplay with solar winds that results in spectacular auroras. The extreme axial tilt of Uranus also affects how these auroras appear from Earth. Because one pole always faces the sun while the other is shrouded in darkness, the visibility of auroras changes dramatically throughout Uranian seasons. During summer solstice on Uranus, When one pole basks in continuous sunlight for over 2 decades, auroras can be particularly vibrant and visible from Earth. However, during winter solstice, the polar regions experience extreme darkness, making it challenging to observe these luminescent phenomena from our vantage point. These variations in aurora visibility throughout Uranus's seasons highlight another fascinating aspect of how this sideways-orientated planet experiences climate and atmospheric interactions. By understanding the intricate balance between solar winds, magnetic fields, and planetary orientation, we deepen our appreciation for the unique celestial wonders that Uranus offers. Conversely, when the opposite pole faces the Sun, it experiences 21 years of uninterrupted night, leading to intense cold. This dramatic shift in daylight and temperature creates distinct climate zones on Uranus, with the sunlit pole being much warmer than the dark side. This unique orientation has significant implications for the planet's overall structure and long-term climatic conditions. By understanding these oblique seasons, we gain insight into how Uranus's tilt affects its climate over extended periods of time. This tilt not only shapes the immediate weather patterns, but also influences the broader climatic zones and temperature gradients between the hemispheres. As we continue to explore this icy giant, we come to appreciate the profound effects of its unusual orientation on its climatic conditions and seasonal extremes. One of the most unusual aspects of Uranus is its extreme polar day and night cycles. Meanwhile, the opposite pole plunges into darkness for the same duration, experiencing an equally prolonged night. Uranus lacks the internal heat found in other planets like Jupiter or Saturn, which helps regulate their temperatures. This absence of internal heat is a major contributor to Uranus's frigid conditions. This orientation means that for over 2 decades at a time, one pole is bathed in continuous sunlight while the other remains shrouded in darkness. Imagine standing under an eternal sun or enduring a prolonged night. This unusual setup leads to dramatic temperature fluctuations, creating an atmosphere that is far colder than what we would expect based on Uranus's distance from the Sun alone. The ice giants, like Uranus and Neptune, are already cold, but Uranus takes this to an entirely new level. The extreme tilt also affects the planet's climate stability. With such prolonged seasons, the transition between day and night is abrupt, and the overall atmospheric dynamics become highly complex. Understanding Uranus's unique orientation helps us grasp how a planet's structure and climate can be profoundly influenced by its rotation. This is more than just a celestial body, it's a testament to the intricate balance of cosmic forces. This glimpse into Uranus's complex climate dynamics illustrates how a planet's peculiarities can shape its environment in extraordinary ways. Observations and predictions show that these climatic shifts can significantly alter the planet's atmosphere over extended periods of time. These variations in sunlight lead to bizarre seasonal extremes on Uranus, with one pole experiencing continuous daylight for over 2 decades while the other remains shrouded in darkness. These extreme conditions pose challenges and opportunities for future scientific exploration of the planet. Like Earth, Uranus has an atmosphere composed of several layers, each with distinct properties and functions. At the base lies the troposphere, where most of the planet's weather happens. It's relatively thin compared to Earth's. Above that sits the stratosphere, a layer known for its strong winds and unique storm systems. The tilt causes these winds to blow in unusual directions and at extreme speeds. The thickness of the stratosphere varies greatly due to Uranus's orientation, leading to stark temperature differences between poles. These extreme temperatures and wind patterns driven by Uranus's tilt play a vital role in shaping the planet's overall climate and weather systems. The ionosphere of Uranus, a protective layer in the planet's upper atmosphere, is anything but ordinary. Formed by the interaction of solar radiation and the winds that whip around Uranus at speeds of up to 560 mph, this delicate shell plays a crucial role in shielding the planet from harmful radiation. But it's the extreme axial tilt of Uranus, rolled over on its side, that makes the ionosphere's behavior so complex and unique. Imagine the winds on Earth, which typically reach around 60 mph in a hurricane. Now multiply that by nearly 10 times to get an idea of the forces at play here. This constant bombardment by intense winds, coupled with Uranus's orientation, creates an ionosphere that is both dynamic and unpredictable. During Uranus's summer, the lit pole experiences a surge of charged particles as solar radiation pours down. This creates a thicker, more active ionosphere that is better equipped to protect the planet from harmful cosmic rays. However, when Uranus transitions into its long winter season, the dark pole loses this protective layer. With no sunlight to energize the ionosphere, it becomes thinner and less effective at blocking harmful radiation. These dramatic fluctuations in the ionosphere's density directly affect Uranus's climate and overall stability. When the ionosphere is weak, harmful cosmic rays can penetrate deeper into the atmosphere, affecting weather patterns and potentially causing long-term shifts in the planet's climate. To put this into perspective, that's colder than any part of Earth has ever been. The lowest temperature recorded on Earth was 89 degrees Celsius, still much warmer than Uranus's average temperature. Imagine one of Uranus's poles, a place where the sun shines for over 2 decades straight, and then vanishes into darkness for just as long. These winds sculpt intricate storm systems that are shaped not just by Uranus's internal heat, but also by its axial tilt. This dramatic shift between daylight and night creates bizarre seasonal cycles that defy what we expect from celestial bodies. For a glimpse of how unusual Uranus's climate extremes are, consider this. While one pole basks in eternal sunshine, the other endures continuous night. These conditions create a world where seasons are not just different, but fundamentally otherworldly, a testament to the power of Uranus's unusual orientation. These varied conditions across Uranus's surface reveal an intricate climate variation driven by its peculiar orientation. It's a testament to how Uranus's unusual tilt shapes not just its seasons, but every aspect of its environment. Uranus, with its extreme tilt of 98 degrees, experiences unique climatic conditions. This peculiar orientation impacts the planet's thermal inertia, a property that helps maintain stable temperatures. Imagine Earth tilted on its side. This is what Uranus looks like. With one pole facing the sun almost directly and the other in near total darkness for years, you'd expect extreme temperature swings. However, Uranus exhibits remarkable thermal stability thanks to its high thermal inertia, a measure of how well a body retains heat over time. These winds, driven by Uranus's unique axial tilt and rotation, play a crucial role in maintaining the planet's thermal equilibrium. Despite one pole being perpetually dark for 21 years, Uranus maintains its temperature stability due to this effective heat redistribution system. This thermal inertia and the planet's sideways rotation create a resilient climate that defies expectations, showing how Uranus's unusual orientation is key to its stable environment. Uranus's extreme tilt and slow rotation are not just quirks of celestial mechanics, but essential factors in maintaining the planet's climatic stability. This unique balance of thermal inertia and steady winds is what keeps Uranus from experiencing the wild temperature swings you might expect given its dramatic axial tilt. Did you know that Uranus is home to hydrocarbon lakes? These are not your typical bodies of water. They're composed of liquid methane, ethane, and propane. Unlike Earth's watery oceans, these lakes exist in a world where temperatures can plummet to 207 degrees C, 358.6 degrees F. The formation of these hydrocarbon lakes is a consequence of Uranus's extreme axial tilt and its unique atmospheric composition, which includes traces of methane that give the planet its blue-green color. During summer on the lit side of Uranus, temperatures can rise slightly, causing methane gas to evaporate and condense into liquid form when it cools down. This process is further aided by the strong winds that sweep across the planet's surface. Imagine this: a summer's day on Uranus can last for 21 years, with the lit side of the planet basking in continuous sunlight. During this time, the heat absorbed by the hydrocarbon lakes can evaporate the liquids, creating localized weather phenomena that ripple across the planet. As seasons change and Uranus begins to tilt away from the sun, the temperatures plummet once again. The evaporated gases can then condense back into liquids, leading to a cyclical process that repeats every 84 Earth years, the duration of one Uranian year. These hydrocarbon lakes not only affect local weather, but also influence global climate patterns, albeit in ways that are still being studied and understood by scientists. Their presence adds a level of dynamism to an already complex system of atmospheric layers and seasons. This chapter demonstrates how these hydrocarbon lakes play a crucial role in shaping Uranus's atmospheric conditions, further emphasizing the planet's distinct orientation and climate. The concept of atmospheric blocking is a key factor in understanding Uranus's unique climate patterns. Atmospheric blocking occurs when a large weather system becomes stationary or moves very slowly across the planet, effectively blocking the progression of other weather systems behind it. Strong winds on Uranus can span the entire planet, leading to unique storm systems that behave differently from those on Earth. Observations from the Voyager 2 spacecraft revealed that Uranus's atmosphere is composed of layers that experience significant temperature variations. The troposphere, stratosphere, and thermosphere of Uranus all exhibit distinct temperature profiles that contribute to the planet's atmospheric blocking. These temperature differences drive the planet's unique weather patterns and contribute to the formation of atmospheric blocking systems. This extreme variation creates an environment where weather systems can become trapped in the polar regions for extended periods. As these systems linger, they can block other weather patterns from moving through the planet, leading to atmospheric blocking that is both prolonged and intense. Understanding these blocking patterns provides insights into the intricate workings of Uranus's atmosphere and the profound influence its unusual orientation exerts. In this sideways world of Uranus, the planet's tilt has shaped an atmospheric environment that defies our expectations and offers a glimpse into the complexities of celestial bodies. During summer on Uranus, which can last for 42 years due to its sideways rotation, one hemisphere is bathed in continuous sunlight, while the other is shrouded in darkness. The atmospheric composition of Uranus changes dramatically during this season. The side facing the sun experiences an increase in the abundance of hydrogen and helium, the primary constituents of its atmosphere. On the dark side, these gases become depleted as they condense and freeze out, forming icy particles that sink deeper into the planet's atmosphere. In winter, when the dark hemisphere is facing the sun and the light side is in shadow, the reverse occurs. The abundance of hydrogen and helium increases on the previously dark side, while these gases become depleted on the now lit side. These seasonal variations in Uranus's atmosphere highlight the complex interplay between the planet's orientation and its climate dynamics, creating a celestial environment that defies our earthbound expectations. The resulting temperature differences between these polar regions are stark. While one pole basks in continuous sunlight, the other is plunged into deep freeze. On the sunlit side of Uranus, hot air rises rapidly, creating powerful convection currents that circulate around the planet. In contrast, the dark side experiences a more sedate atmospheric flow, with cooler air sinking gently. This disparity in convection patterns is a direct result of Uranus's unusual orientation and the drastic temperature differences it causes. Understanding these unique atmospheric processes further reveals how Uranus's orientation influences its climate, creating a celestial environment that defies earthbound expectations. It is within these intricate dynamics that the true beauty of Uranus's atmospheric system lies, showing us the complex interplay between tilt and climate. Uranus's polar regions, unlike those of other planets, are not shrouded in a perpetual veil of cold darkness. Instead, these areas are subject to extreme fluctuations in temperature and daylight. One such phenomenon is the formation of massive storm systems that can span the entire planet. These weather events are not just anomalies, they are a direct consequence of Uranus's unusual orientation. Understanding these extremes gives us a glimpse into the intricate interplay between tilt and climate. Uranus's extreme tilt of nearly 98 degrees introduces unique dynamics into its atmospheric vortices. The planet's sideways orientation affects the formation, behavior, and lifespan of these complex weather systems. Atmospheric vortices are spinning columns of air that occur in various forms across different planets. On Uranus, they manifest as powerful storms driven by the planet's unusual orientation. Due to Uranus's tilt, its poles face the Sun continuously for 21 years during summer. This extreme sunlight exposure contributes to the formation of massive polar vortices. The magnetic field's interaction with charged particles in Uranus's atmosphere can lead to the formation of unique vortices that defy our expectations of traditional weather patterns. Observations by spacecraft such as Voyager 2 have revealed these atmospheric phenomena, providing insights into the profound impact of Uranus's tilt on its climate dynamics. Scientists continue to study these vortices to understand how they shape Uranus's unusual weather patterns and contribute to its extreme temperature variations. The planet's tilt orients these vortices in a way that creates distinct wind patterns across the globe, contributing to Uranus's unique and dynamic climate system. By examining these atmospheric vortices, we gain a deeper appreciation of the intricate interplay between Uranus's tilt and its climate patterns. Ultimately, the tilt of Uranus not only defines its orientation, but also plays a crucial role in shaping the atmospheric dynamics that make this planet so extraordinary. During this period, thermal flux, or the redistribution of heat, plays a crucial role in shaping Uranus's climate zones. As a result of this thermal flux during different seasons, heat is redistributed across the planet in complex ways. Despite the harsh conditions, Uranus still exhibits a dynamic climate with distinctive zones that are shaped by this thermal flux. To understand how these zones form, consider the polar regions of Uranus, where temperatures can vary dramatically due to the planet's tilt. Thermal flux in these areas ensures that some parts of Uranus experience near constant sunlight, while others remain in darkness for extended periods. This unusual orientation allows Uranus to maintain its unique seasons and extreme temperature variations, which are crucial for the planet's overall structure and stability. One of the most fascinating phenomena resulting from this sideways rotation is the formation of unique atmospheric blocking patterns. These blocking patterns are characterized by high-pressure systems that disrupt the normal westward flow of air currents. On Uranus, these high-pressure zones can persist for extended periods, leading to stagnant weather conditions and unusual storm patterns. Comparing Uranus to other planets like Earth and Mars, which have more conventional tilts, highlights the stark contrast in weather stability. On Earth and Mars, atmospheric blocking patterns can cause severe weather events, but they are typically short-lived due to the planet's more balanced axial tilts. Uranus, however, experiences prolonged atmospheric blockages that can span entire seasons, causing sustained extreme weather conditions. This unique orientation and the resulting blocking patterns challenge traditional climate models, offering a glimpse into the complex dynamics of planetary weather systems. This unusual magnetic setup plays a crucial role in shaping Uranus's atmosphere. During different seasons, the planet experiences significant shifts in its atmospheric composition due to these magnetic fluctuations. Scientists believe that these seasonal shifts in atmospheric composition are driven by Uranus's complex magnetic field and its interaction with solar winds. The offset magnetic field allows for unique reactions between the atmosphere and charged particles from the Sun. Understanding these shifts provides valuable insights into the intricate dynamics of planetary weather systems and their dependence on magnetic fields and seasonal changes. On Earth, this process is fairly straightforward. Warm air rises, cools, and sinks again. But on Uranus, the 98-degree tilt disrupts this simple pattern. The planet's sideways rotation causes convection currents to form and behave in ways that are distinct from Earth's patterns. Heat distribution on Uranus is a complex dance, with warm air rising along the planet's highly tilted axis and cooler air sinking. This process creates unique wind patterns and atmospheric circulation. Comparatively, Earth's winds are much milder due to its more balanced axial tilt and internal heat generation. In this dynamic interplay, we see how Uranus's unusual tilt not only defines its seasons, but also influences the very currents that carry heat across its surface. This intricate dance between Uranus's axial tilt and atmospheric convection offers a glimpse into the deeper complexities of our universe's weather systems. And as we continue to explore these distant worlds, each discovery brings us closer to unraveling the mysteries that lie beyond our own pale blue dot. At one pole, temperatures can plummet to 1970 cc's, 32 degrees C5, while at the other, they rise to a relatively balmy 11145 dCc, Su 229 degrees C5 kinds. This massive temperature swing sets the stage for powerful storms that can sweep across the entire planet. Observations from Voyager 2 revealed that Uranus experiences intense wind speeds reaching up to 900 kph 60 mph. The polar regions bear the brunt of these storms, with turbulent weather patterns that challenge our conventional understanding of planetary climates. As Voyager 2's data showed, the combination of Uranus's unusual orientation and its rapid rotation contributes to these intense weather patterns. These waves are unlike anything we see on Earth. They snake around the planet, driven by its extreme axial tilt and powerful winds. Uranus is not only tilted on its side, but also rotates in a retrograde direction, east to west, making its weather patterns highly unusual. Scientists believe that the orientation of these waves is profoundly influenced by Uranus's tilt. The waves often align with the planet's equator rather than its poles. This orientation defies traditional expectations based on Earth's weather patterns, where waves typically align with the poles due to our planet's more standard tilt. The extreme tilt and retrograde rotation of Uranus cause the waves to form in unexpected directions. These atmospheric waves have significant implications for Uranus's climate and overall structure. They contribute to the planet's bizarre seasonal extremes. Conversely, during winter, when one pole is shrouded in complete darkness for an equally long period, these waves help to disperse the remaining heat. In this way, Uranus's atmospheric waves are integral to maintaining a delicate balance in its extreme climate conditions. The dynamics of these waves underscore the deep-seated effects of Uranus's tilt on its overall atmospheric structure. This sideways rotation creates intense vertical wind shear, where winds at different altitudes blow in opposite directions. As air rises and falls on Uranus, these conflicting winds can cause turbulence, creating unique storm systems that span the planet. Scientists believe the extreme temperature variations on Uranus drive these winds, creating unique climate patterns over time. It's this intricate dance of wind shear and extreme climate shifts that makes Uranus a fascinating laboratory for studying unusual weather patterns. Understanding these dynamics deepens our grasp of how celestial bodies can defy conventional expectations, all due to their unique orientations. It's not just Uranus's sideways roll that makes it unique. The planet's extreme tilt has profound effects on its upper atmosphere, causing a phenomenon known as mesospheric turbulence. This is where things get interesting. The combination of Uranus's tilt and its offset magnetic field leads to mesospheric turbulence, chaotic winds that blow at altitudes ranging from 50 to 90 kilometers. Imagine a planet where one pole basks in sunlight for 42 years straight, while the other remains cloaked in darkness for the same duration. This extreme variation is no fantasy, it's Uranus's reality. The temperature fluctuations between the poles are so dramatic that they trigger powerful winds high up in Uranus's atmosphere, the Mesosphere. These turbulent winds aren't just a curiosity, they have real consequences for the planet. They can scatter and mix gases in Uranus's atmosphere, affecting its overall climate. In fact, these winds are thought to play a role in redistributing heat on Uranus, contributing to the planet's complex climate patterns. But what makes this all the more fascinating is that these winds are a direct result of Uranus's tilted orientation. It's as if the planet itself is in a constant state of unrest due to its unusual positioning. This layer of complexity added by Uranus's orientation shows how a planet's upper atmosphere and climate can be profoundly shaped by its unique tilt. The magnetic field generated by electrically conductive fluids in Uranus's interior is also tilted, creating a complex interaction with the solar wind. This interaction results in unique auroras that dance across Uranus's poles, their vibrant displays a direct consequence of the planet's peculiar tilt. The solar wind, a stream of charged particles from the sun, usually strikes planets at their magnetic poles, but Uranus's off-kilter orientation scrambles this pattern. Instead of a predictable interaction, the solar wind slams into Uranus at various angles, causing dramatic and unpredictable auroras. These auroras are not just a cosmic light show. They also affect nearby celestial bodies by altering the magnetic environment in space. Satellites orbiting Uranus can experience glitches or system errors due to these sudden changes in magnetic fields, highlighting how Uranus's tilt influences broader space weather. Though far from Earth, the unique magnetic interactions at Uranus offer a glimpse into the complex dance of planets with their environment. Understanding this dance is crucial for predicting space weather and safeguarding technology in the cosmic frontier. Uranus's tilt doesn't just shape its own climate, it reshapes the very fabric of space around it, illustrating how a planet's orientation can profoundly influence its cosmic neighborhood. The combination of this icy climate and Uranus's unique tilt leads to extraordinary temperature differences between the lit and dark poles. Among these phenomena are the planet's polar jets, strong winds that blow from one pole to another, driven by the heat differential between the lit and dark poles. During summer at the lit pole, temperatures can soar as high as 176 degrees C 285 SW, while during winter at the dark pole, they plummet to a frigid 216 degrees C 359 degrees SW. These temperature differences drive powerful winds that funnel heat from the warmer lit pole to the colder dark pole, creating strong polar jets. These polar jets play a crucial role in shaping Uranus's climate by helping to even out the extreme temperature differences caused by its unique tilt. Despite their strength, these polar jets cannot fully compensate for the planet's enormous temperature swing. By understanding the role of these polar jets, we gain insights into how Uranus's unusual orientation shapes its overall structure and climate under its extraordinary conditions. To understand how these oblique seasons impact Uranus's climate, scientists study models that simulate the planet's complex weather systems and temperature variations. This research helps deepen our understanding of the unique climate patterns on Uranus. The exploration of Uranus's oblique seasons not only enhances our knowledge of this distant world, but also challenges us to think beyond Earth-based norms, broadening our understanding of the cosmos as a whole. Meanwhile, the dark pole endures endless night, plunged into a chill that reaches 217 degrees Celsius, 358 degrees Fahrenheit. The vast difference in sunlight exposure leads to stark contrasts in weather patterns across the planet. Understanding these extreme polar cycles provides valuable insights into Uranus's atmospheric dynamics, influenced by its sideways rotation. It challenges us to rethink our Earth-centric norms and broadens our cosmic perspective. The intense cold of Uranus is partly attributed to its vast distance from the Sun, but its atmospheric composition, a mix primarily of hydrogen and helium with traces of methane, also plays a significant role. In contrast, the pole in darkness experiences intense cold, leading to the formation of distinct weather patterns that span the entire planet. These systems are driven by the extreme temperature variations caused by Uranus's unusual orientation. The distribution of heat and moisture is not uniform on Uranus, thanks to its unique wind patterns. These winds help transport heat from the lit pole to the dark one, creating a complex climate system that defies traditional expectations. This intricate atmospheric circulation driven by Uranus's tilt provides valuable insights into how planets with unconventional orientations can still sustain dynamic weather systems. Understanding Uranus's unique wind patterns challenges our Earth-centric perspectives and broadens our understanding of celestial dynamics. As we delve deeper into the mysteries of Uranus, each discovery invites us to rethink what is possible in our vast and diverse cosmos. Exploring how Uranus's tilt influences atmospheric circulation not only deepens our appreciation for the planet's unique climate, but also underscores the beauty and complexity of our celestial neighbors. By studying Uranus, we gain a broader understanding of the cosmos and the diverse phenomena that shape it. Uranus's extreme axial tilt is one of the most unusual aspects of this distant world, leading to severe weather events that defy our expectations. Its sideways rotation creates unique storm systems that can span the entire planet, driven by powerful winds and vortices. These high-speed winds shape the weather patterns on Uranus, forming vast vortices that can wrap around the planet's poles. One of the most striking features of these vortices is their size. They can stretch across entire hemispheres. Think of a giant storm that can cover an area equivalent to the continental United States. The sheer power and scale of these weather systems are a direct result of Uranus's bizarre orientation. These extreme weather phenomena serve as a stark reminder of how much we can learn from studying distant worlds like Uranus. Imagine a world where day can last for 42 years and night even longer. This is not some far-off fantasy. It's the reality of Uranus. As Uranus rolls around the Sun on its side, it experiences a phenomenon known as thermal inversion. This peculiar condition means that Uranus's polar regions can be warmer than its equatorial areas. This prolonged exposure to sunlight can cause temperatures to rise slightly, creating a thermal inversion. The lack of sunlight during this extended period results in exceptionally cold temperatures. This thermal inversion phenomenon is a stark reminder that the dynamics of distant worlds can defy our expectations. Understanding Uranus's unique climate peculiarities sheds light on how the planet's structure influences its atmospheric behavior. So next time you look at the stars, remember that Uranus is out there, rolling on its side and defying all our preconceived notions about celestial bodies. And that, perhaps, is one of the greatest wonders of our cosmic neighborhood. Uranus's unusual orientation, tilted nearly on its side, isn't just a quirk of astronomy. It profoundly influences the planet's climate and atmospheric chemistry. At first glance, Uranus might seem like any other gas giant shrouded in a thick atmosphere primarily composed of hydrogen and helium. Yet, the extreme cold of this distant world is not solely due to its distance from the Sun. The atmospheric makeup of Uranus is not merely a passive reflection of its environment. It actively influences and is influenced by this sideways orientation. Methane, one of the trace gases in Uranus's atmosphere, plays a crucial role in shaping this planet's distinct blue-green hue, a phenomenon unique to Uranus among the gas giants. This extreme tilt causes Uranus's atmosphere to undergo dramatic shifts in temperature and pressure, triggering complex atmospheric chemistry that defies what we expect from celestial bodies. The unique atmospheric conditions shaped by Uranus's axial tilt contribute to its distinct climate and weather patterns that are as much a product of the planet's orientation as they are of its distant solar orbit. And therein lies the wonder of our cosmic neighborhood. Each planet, each tilt, each atmospheric composition, all intricately interwoven to create worlds that are not just distant bodies of light and dark, but complex ecosystems teeming with their own unique stories. The intensity of these interactions can be astonishing. Imagine lightning, but on a planetary scale. These high-energy events sculpt Uranus's atmospheric composition, altering the distribution of gases like hydrogen, oxygen, and nitrogen. Over time, these auroral displays leave their mark on Uranus's atmosphere, shaping its chemical balance in ways that scientists are only beginning to understand. The constant barrage of solar wind and the planet's peculiar tilt create a dynamic interplay that paints Uranus's skies with vibrant hues. So, next time you look up at the night sky, remember Uranus, this peculiar planet with its tilted axis, bizarre seasons, and stunning polar light show. Each flash of light is a reminder of the complex interplay of forces that shape our universe's most distant corners. AGWs are large-scale waves that occur within the atmosphere of a planet. They are created by disturbances in the air and can influence weather patterns over vast distances. These AGWs can span thousands of kilometers, influencing both local and global weather patterns on Uranus. They help to redistribute heat and momentum across the planet's atmosphere. Scientists believe that the interaction between the planet's unique magnetic field and these AGWs can lead to unpredictable weather patterns and climate variations. By understanding how Uranus's sideways rotation influences AGWs, we gain deeper insights into the complex dynamics that shape its climate and weather systems. Each flash of light in Uranus's polar light show is a testament to these dynamic forces at play, guiding us through the mysteries of this extraordinary planet. As we continue our exploration of Uranus and its intricate atmospheric processes, we are reminded of the beautiful complexity that exists within our universe. Did you know that the extreme tilt of Uranus causes unique atmospheric blocking patterns? This phenomenon, known as atmospheric blocking patterns, is a sideways dance that shapes Uranus's climate and weather systems in unexpected ways. This stark contrast in temperature and daylight conditions gives rise to Uranus's unique atmospheric blocking patterns. Atmospheric blocking occurs when a high-pressure system, known as an anticyclone, stalls in place and blocks the progress of other weather systems. On Uranus, these anticyclones can persist for extended periods due to the planet's unusual rotation and tilt. Scientists believe that the persistent nature of these atmospheric blocks can lead to prolonged periods of stable weather on Uranus, lasting for decades or even centuries at a time. Despite their significance, understanding these atmospheric blocking patterns remains a challenge for scientists. The complex interplay between Uranus's axial tilt, its distance from the Sun, and its unique atmospheric composition makes it difficult to model these phenomena accurately. And as we delve deeper into the secrets of this distant world, we find ourselves in awe of the unexpected climatic behaviors that shape the universe around us. This extreme orientation creates unique pressure gradients in the planet's atmosphere. Imagine holding a basketball under your arm. That's how Uranus lies relative to the Sun's rays, causing uneven heating. The result is strong wind patterns and weather systems that can span the entire planet. This prolonged exposure and shadowing creates significant temperature differences across the planet's polar regions. The unusual gravitational distribution on Uranus is another anomaly caused by its tilted orientation. Understanding Uranus's atmospheric pressure helps explain its unusual weather patterns and extreme seasonal changes. Beyond the familiar blue glow of Earth's aurora, Uranus hosts a mesmerizing polar light show that defies our expectations. This unique spectacle is powered by the solar wind, a stream of charged particles that continually bombards Uranus's atmosphere. When these particles collide with the planet's magnetosphere, they excite its atoms, triggering a cascade of chemical reactions. This process creates dazzling displays of polar lights, the polar light show that illuminates Uranus's skies. But the sideways orientation of Uranus adds a twist. Its extreme axial tilt means that the polar lights are seen at unusual angles. The tilt causes unique chemical pathways to form in the planet's upper atmosphere, pathways that might not exist on a world with more traditional orientation. These pathways influence local weather patterns, creating conditions that scientists are still working to fully understand. So, the polar light show on Uranus isn't just a beautiful display, it's also a critical factor in shaping the planet's atmospheric dynamics. And understanding this dynamic is key to unraveling the mysteries of Uranus's unusual climate and weather patterns. And that's just the start of the story. There's so much more to uncover in this enigmatic realm. So, let's keep exploring. Who knows what wonders await us in the depths of Uranus's strange and beautiful skies? This unusual configuration leads to some fascinating atmospheric phenomena. These waves are created by the planet's sideways rotation and its complex magnetic field. As Uranus rotates, it drags a huge part of its atmosphere along with it. This causes the air to compress and expand, generating waves that travel around the planet's atmosphere. Imagine a vast sea of gas with massive ripples rolling across it. These atmospheric waves aren't just a beautiful sight, they play a crucial role in shaping Uranus's climate. Their formation is a result of planetary oscillations, which are a natural consequence of the planet's tilted axis. These oscillations can affect the stability of Uranus's climate by redistributing heat and energy across its surface. This extended period of sunlight can create intense heat waves that spread across the planet. During this time, atmospheric waves become even more pronounced as they help to dissipate heat. When winter returns, the atmosphere's complex dance cools down Uranus's surface. This cyclical process maintains a delicate balance in the planet's climate. And so, as we delve deeper into the mysteries of this sideways planet, we find that its strange orientation creates not only unique weather patterns, but also ensures a remarkably stable climate.